Hello again. Here we are starting with chapter 8. This is lecture 5 for EIR this semester. And now we're going to look at second order circuits. In other words, where you've got a resistor, inductor, capacitor. Well, you basically just need two storage elements. We're going to look at a couple of circuits just now. Okay, for those of you who are wondering, yes, this is the same shirt as in this previous lecture because I'm doing the recording on the same day. Anyway, so we're going to look at the following type of circuits here. So they've got it listed. Let's go to this one. We're going to look at this screen. Stupid. There we go. We're going to first, for today, we're just going to focus on the second point and on how to determine initial and final values, because that is the key to solving this whole chapter. Then we're going to look at the source-free series RLC, source-free parallel RLC. Then step response for a series RLC and a step response for a parallel. And we're quickly going to look at general second order circuits. Now, what do I mean with you actually only need two energy sources? So here are the two circuits that we're going to focus on primarily, the series and the parallel circuits. But when we get to the general order circuits, we're going to look at that you can also get a second order circuit by just having two elements, two inductors. But the snag with this circuit is we can't combine those two inductors into one inductor. So they remain two separate. And the same for the two capacitors here. There's a resistor in the way, so we can't combine the two capacitors into a single capacitor to just get a first order RC circuit, or on the top so we can get a first order RL circuit. So that remains second order circuits, but we're going to focus on these two scenarios, or four scenarios: series and parallel, source free, and step response. So let's go to chapter 8.2, and you're going to see there we're going to focus on just finding the initial and final values. And as the textbook describes there, that is because that is the part that students mostly struggle with in this chapter, is finding the initial conditions. At the end of the chapter, you're going to see this whole thing is just a recipe that you're going to follow, depending on how they're connected and a couple of other things. But if you can't determine the initial conditions, you go to the next question. Okay. So we're going to look at VO0, I0 that we've already done, and then the VDT over here, the IDT as well. But there are two key points that we need to keep in mind the whole time, and for that I'm going to go over to the board. So while we're going to do chapter 8.2 and we're going to learn how to calculate those initial and final conditions for RLC circuits, there are two key points that the textbook also mentions that we need to take into account. The first key point is the assigned polarity, or the passive sign convention that we need to apply. So point 1 is just passive sign. Now I know we've already spoken about this as we went through, but here it's going to become absolutely critical. So let's say, first let's look at a capacitor. Now when we're going to look at capacitors, we typically want to know what the voltage is across the capacitor. So plus, minus, VC. And the textbook also now states when we're talking about V, it's the capacitor voltage. And if it's I, it's inductor current. Now since they specify the voltage across the capacitor, the polarity, it implies the direction of the current, and current flows through a passive element in from the plus to the minus. So that will be the direction for the current. Why is this going to become important? Because we're going to do Kirchhoff current laws, we're going to do KVLs, and then we need to know what the currents are. And then for the inductors, For inductors, they typically specify the direction of the current through the inductor. Now, if the current is specified, it implies that the voltage has to be plus minus V of L. So that's I of L, I of C, V of C. That indicates or implies through the passive sign convention what the direction or the polarity of the voltage must be. So that's the first thing. Then point number 2, or that critical point, what do they call this? The continuity in the voltage and the current. So all they mean there is what we've already drilled in over and over, that VC0 plus must equal VC0 minus, and IL at time 0 plus must equal I L at time 0 minus. So that is just the continuity in order to determine the initial and the final condition. So that's actually nothing new, and now the textbook only in chapter 8 states that time 0 plus is the time just after the switch is closed or something is switched, and time 0 minus is just before, right? But we've already introduced that concept in chapter 7. Okay, so the best way is we're going to run through 3 problems. 2 of them are going to be examples that's in your textbook, that I'm going to probably just write it out a bit different than what the textbook does, so that you can just get used to our notation, and then we'll take it from there. So we're going to start with example 8.1. There's 3 parts to the question. The first part, we're going to just find the initial current and initial voltage across the capacitor and through the current. Which direction is the current going? In that direction, A. That direction. Then we're going to look at to find the initial conditions for the 2 derivatives. In other words, the IDT and the VDT, and then the time infinity. Right, so there's the 3 sets of conditions. So with the first order circuits, we just had to find the initial current or voltage and time infinity and the time constant. Now, there's these 2 initial conditions plus the dVdt, the IDT initial conditions, and there's the infinity values. So let's start. This we should be comfortable with. We just have a 12-volt source, a switch that opens at time 0. So we need to go and look at what is happening at time 0 plus. Now remember that second point, that I0 plus and V0 plus, VC0 plus must equal the same values at time 0 minus. So let's go and look first. Which one did I first look at? So we're going to look at time 0 minus. So at, doesn't want to write in this corner still. No, it's the chalk. Something's not like with the chalk. At t equals 0 minus. What do we have? So just before that switch opens, we'll have a steady state. What happens in steady state? In steady state, an inductor becomes a short circuit and a capacitor becomes an open circuit. So then our circuit is going to look as follows. The resistor is there. The inductor is a short circuit. The resistor is there. The switch is still closed at time 0 minus. So I draw the switch closed. And the capacitor is an open circuit. So our switch at our circuit at time 0 minus looks like this. So we still have the 12 volts. We've got the 4 ohms over there. What is this one? 2 ohms. Okay. There is our voltage, our VC. I like to write in VC and all the, otherwise I get confused. And there's my inductor current. Alright, so we need to go and calculate those 2 values. The current is an easy one. If we've got 12 volts here, where's the source is going to push a current into the circuit, which is the same current that's going to flow through the inductor. That current gets to this node. It sees 2 ohms. It sees an open circuit. So where's it going to flow? All the current has to go through that 2 ohms. So this is effectively just a series circuit. So we have that I0 minus equals the 12 over, what was that? 4 plus 2. They really make it nice and easy, hey? And now if only the chalk will work. We've got 2 amps. Right, so that is at time 0 minus, and then which is also the value at time 0 plus for the current. So let's say that is then also I0 plus. Okay. And then what is VC at time 0 plus must equal VC at time 0 minus. What will that be? The voltage across the capacitor is now the same as the voltage across what other element? Across this 2 ohms, because they are sitting in parallel now with that switch closed. So if I can find the voltage across the 2 ohms, I know what the capacitor voltage is. Now there's more than one way, of course, you can do this. You can simply take this IL that you've calculated and multiply it with the 2 ohms to get it 2 times 2 gives you 4 volts. But the snag with this, if you use this method, is that you are relying on a previous calculation. So if you made a mistake over here for some wacko reason, then this answer is also going to be wrong. All right, so then it just snowballs. So my advice in this chapter, and pretty much for all the work in this entire course, and well, your whole way forward, is if you can calculate a parameter by using only what was given, and then you're safer than using what you have calculated. So stick with what you've been given as far as possible. So can we get this voltage across the 2 ohm with just what's been given? So we've got those 2 resistors still in series. So I can do a voltage division. 2, there's the 4, and there's the 12. So I'm going to write, I want the voltage there, so it's going to be the 12 volts times the 2 ohms, because that's the resistor across which I want the voltage, and then becomes 2 plus 4. So that's 2 over 6, it's 1 over 3, so 12 divided by 3 gives me 4, what's it now? Volts. Okay, so there we've got those 2 covered through a simple current. Something missing here, hey? No. What did we do with this one? Oh yeah, just Ohm's law. I'm looking for a current division or a voltage division here. This is just simply Ohm's law to get this one, and for the current and for the voltage we use the voltage division. Okay. How much space do I need for the next one? The next one we're going to need a little bit more space. So I just want to see. Yeah, I'm going to clean out this one. Okay. So that's sorted for the A part. So now we know, hey, we've got these 2. All right. In the B part, they want us to find let's keep it in the same order, yeah, dI dt at time 0 plus, whoopsie, time 0 plus, and they want us to find dV dt at time 0 plus. What do those expressions mean? Let me just get some other chalk here. What is this in English? The IDT is the rate of change of the current. dVdt is the rate of change of the voltage across the capacitor. In other words, what they want us to calculate physically, remember we're modeling, we're taking physical stuff and writing it in terms of mathematics. And this expression tells me I want to find out at what rate is the current through the inductor changing the moment that switch flicks open. And at what rate will the voltage across the capacitor be changing the moment that switch opens? Just for that brief moment. Because remember, when the switch switches, we're going into a transient period before we reach our new steady state. So we just want to figure out how fast is it changing. And why do we want this? That will become apparent when we get to chapter 8.3. Okay, so let's focus on the IDT first. How do I get the IDT? Now for this you need to go, actually we need to go back to your chapter 6. So we know that the voltage across an inductor, equals L di dt. And now we're looking for this di dt. So in other words, if I want di dt at time 0 plus, I need to simply find VL over the inductance. But what VL am I looking for? I'm looking for VL at time 0 plus because I want the IDT at time 0 plus. So if I can find the voltage across the inductor, the moment that switch opens, I know what that rate is. So for this we need to go and redraw our circuit for our new condition. Well, with that switch open, I think for the sake of space, I'm not going to do it. We don't need to. So what is this circuit going to look like for time greater than 0? We're simply going to remove that part of the circuit because that switch is open. We know there's not going to be any current flowing through there, so we're sitting with that scenario. So where is this voltage across the inductor? Now this is where that passive sign convention rule comes in. They've already given us the direction of the current. So if the direction is left to right, it means I must have plus, minus, now that 0.25 is in the way. Okay, plus, minus, let's just write the 0.25 henries over there, VL. See now, if you make the mistake here of getting that polarity wrong, then obviously the sign of the year is going to be wrong, so that's not going to work. So it's important, if the current is in that direction, left to right, then I need plus and minus. Okay. So what is that voltage going to be? I'm looking for a voltage in this circuit. So typically if you want a voltage, let's do a KVL. Where, Larry, where? I don't want to sickle with the writing. And I'm going to need some space. I'm going to do it here. Okay. So we're going to do a KVL around our circuit. So we come in at this one, a minus 12. So it's minus 12. Then it is, the current goes through the 4 ohms. So it's plus 4. And then I, what current? Well, we're all working now at time 0 plus. So it's going to be I at time 0 plus. Then it's into VL, plus VL. Then we're going to go through the capacitor also entering on the positive terminal. So it's plus VC, and all of this has to equal 0. Right. Do we know what I0 plus is? Yes, we calculated that in the previous one. I don't have it on the board anymore, but this was 2 amps. Okay. We calculated that as 2 amps. Do we know what VC? Oh, I should write this as 0 plus. As a 0 plus equals 0. Yes, we calculated that VC 0 plus as well, and it was 4 volts. At 4 volts. So now you can see why it's important that you first get those two values, because you're going to need it when you start calculating the derivative initial conditions. So let's substitute. So we've got 4 times 2 plus VL plus 4 equals 12. Okay, so 8, 12, 12 minus 12 gives you 0, so VL equals 0 volts. Well, perhaps we should let me rather write it like this. VL at time 0 plus equals 0 volts. So just for that very brief point in time, you've got 0 volts sitting there. Substituting this now back into this equation, it means we've got 0 over, well, I don't care what the L is now, 0.25. That gives me 0. And what's the units? The units are in, look at your DIDT, it's current at the top, time at the bottom. So it's amps divided by seconds. Amps divided by seconds. Now perhaps someone at this point, when you get a unit like this, amps divided by, you can't, in the spreadsheet that you guys are going to do, you can't do a streepie, a normal divide by. When we did OCRs, we had to write it as amp divide by seconds because the OCRs doesn't take this, but you should know that from EBN. So in the spreadsheet, it becomes a little bit more tedious. You need an ampersand divide semicolon seconds. Okay, so the moment you want to divide, you need to write this out. But don't worry, I'm going to give you like a drop-down menu that you can select the units from. Otherwise, I'm just going to give you the units. I'll see what's the least pain. Okay. Okay, so that sorts out the DIDT. So now we've got that one. Now we need the DVDT. So how do I get DVDT? Again, chapter 6 actually. So we know the current through a capacitor equals C dVC dt. Right, so that's from chapter 6. So you actually still need that theory, lo and behold. Let me just page over. My fingers though want to grip with a chalk on it. Okay, there we go. So here's the dVc dt. So in other words, dVc dt at time 0 plus must then equal this IC at time 0 plus divided by the capacitance. Now, how do I get IC 0 plus? Back to this circuit. Here's the voltage across the capacitor. So where's the current through the capacitor? Well, it's plus at the top, so the current through the capacitor will have to flow down. How am I going to calculate this IC looking at my circuit diagram? And now you need to notice that, wait a minute, everything here is connected in series. So the capacitor current must always be the same as the inductor current. So if I can find the inductor current at time 0 plus, I know the capacitor current. In other words, IC at time 0 plus must equal IL at time 0 plus. And that we actually calculated in the very first part, and we saw that it was 2 amps. So that comes from the first bit, so we know that is 2 amps. So now we can substitute this back in here. So we've got 2 divided by, what's the capacitance? 0.1, 0.1. So we've got not enough space to write this thing out. So I'm just going to dVc 0 plus equal divide by dt is then 2 over 0.1 equals 20. And the units, dV, volts at the top, time at the bottom. So it is volts per second. So the current initially changes at a rate of 0 amps per second. And the voltage, the moment that switch flicks open, will change at 20 volts per second. But that only applies for that split second of 0 plus, just that instance directly after. Okay, so now we've got the initial conditions for the rate of changes. The next thing for the C part, we now need to go and calculate the steady state or the final value at time infinity for the two. So in other words, for the C part, we're going to find I at infinity and we're going to find V at infinity. So what is this circuit going to look like at time infinity? Inductors become short circuit, capacitors become open circuit. So let's redraw it over here. So we've got plus minus, you've got that resistance, the inductor is a short circuit, and the capacitor is a open circuit. So here we've got 12 we've got 12 volts, 4 ohms, and the current is still flowing in that direction, and I've got plus minus VC over there. Right. What is that current going to be at time infinity? Can you have a current flowing in that circuit? No. Why not? Because there's this gaping hole in my circuit, pothole, or no, that's worse than a fallen bridge. Right, so the current can't flow. So that means at time infinity, you've got 0 amps. Right. Voltage. What is the voltage across that cap? How do you calculate it? Do a KVL, right? So we're going to do a KVL quickly for this circuit. If you can't just write out, see it, because this is very much like we did in chapter 7. So you end up with minus 12 plus, well, we know the current is already 0, so it's 0, and then plus VC, and all of that must add up to 0. So in other words, VC at time infinity is simply going to be 12 volts. So this source is just going to charge up that capacitor until you've got 12 volts there, 12 volts there, no potential difference across this part of the circuit, so you can't have any current flowing, so that's effectively the capacitor acting then as an open circuit. Okay, that's example 8.1, which is a fairly simple one. Let's move on to the next problem. Okay, we're going to do practice problem 8.1. What do we have? We've got a 2 ohm resistor, we've got a capacitor parallel with that resistor, 1/20 farad, and there's the voltage, plus minus. A 10 ohm resistor sitting parallel with that 10 ohm resistor is a switch that closes at time 0. So at time 0, we're going to short out that resistor. A 0.4 Henry inductor, and that is connected in series with this 42 volt source. And there's the current flowing in that direction. So perhaps someone now already, if the current is flowing in that direction, we know the voltage across the inductor is VL is going to be in that direction. And if the capacitor is plus minus, we know that IC will be flowing down through that capacitor. We know we're going to need that, so I'm somewhat putting that in immediately. So we're going to go through the same steps. We're going to find the initial current and voltage, then the initial derivatives, and then the time infinity values. So let's do first part. So let's find which one did I start with? I0 plus. I0 plus and V0 plus. So again, we need to, if we want the 0 plus values, we need to look at time equals 0 minus. What did that circuit look like? Now, time 0 minus, that switch is still open. Capacitor will be open circuit. Inductor will be short circuit. Right. So we redraw the circuit. And then the capacitor is open. The switch is open, so the resistor is there. The inductor is a short circuit, and then you've got the voltage source, plus, minus, that source, right, and the inductor current is flowing over there. We've got plus, minus V over there, and 42 volts, and we've got 10 ohms, and we've got another 2 ohms over this side. Okay, what is the easiest one? Let's do the current again first. So I0 plus must equal I0 minus, because the current can't change instantaneously. Looking at this circuit, everything is just connected in series. So we've got 42 divided by the 10 plus 2, which is 42 divided by 12, which is not a pretty nice round number. So that's a 3.5 amps. What time is it now? It's 10 past 4, so my brain doesn't want to think that lekker anymore. Okay, so we've got 3.5 amps, and then for the capacitor, 0 plus must equal the capacitor voltage at time 0 minus. So let's look at what that's going to be. What's the voltage across the capacitor? Well, it's parallel to this 2 ohm. So if I can find the voltage across the 2 ohm, and again, what's the word? way of thinking as the previous round, reasoning. You can either now use your 3.5 amps and just multiply it by the 2 to get your 7 volts. But that's now using your own calculation. So in principle, it's better to use what you've been given. So let's do a voltage division. So it's 42 volts. And that's going to split between the 2. Whoa, that's supposed to be a 2. 2 over the 10 plus 2. So that's a sixth. And that gives me 7. Yeah, 7 volts. Right, so now we've got those two first initial conditions. So let's keep that there. Okay, so that's for just the voltage in the capacitor. So for the B part, so this was for the A, we're going to find the derivative conditions. So now we want, I'm going to need a new circuit. So now we're going to solve for the IDT, the I 0 plus dt, and we need to solve for dv dt also at time 0 plus. So what is that circuit going to look like? So now we're working at time 0 plus. So at time equals 0 plus, what will the circuit look like? Well, that switch will be closed now. So the resistor then disappears out of the circuit. So we have to redraw again. So that remains there. The capacitor is still there. Now I am not drawing the capacitor as an open circuit now, like we did over here, because we're at time 0 plus, we're entering the transient condition, not a steady state. So the capacitor is there. Then that switch closed, shorts out the 10 ohms. So I'm just going to draw a short circuit for that one. Then we have, why doesn't the chalk want to write now? And the inductor, and we still have our source over there. Right, and we've got plus minus V, which means the current is in that direction. This is still 2 ohms, and then plus minus, well, the current is given in that direction. There's my current, so it's plus minus VL, and we still have the 42 volts. Okay, so starting with the current, how do we solve for the current? If it's dIdt, you need to think VL equals L dIdt. So yes, you're going to have the equation in your textbook, but it's probably going to take you more time to look it up there. So in other words, we have that dI dt at time 0 plus equals VL at time 0 plus divided by the inductance. Now what is this voltage at time 0 plus? So we need to solve for a voltage. So the easiest is if we're going to do a KVL in that loop. So if we go in this direction, we enter the 42, so that's minus 42, then plus VL, then plus VC. That must all equal 0. I'm not going to write VL 0 plus and VC 0 plus. We know we're working at time 0 plus. All right, so VL 0 plus, which is what we want, must then equal the 42 goes to the other side. Then do we know what VC at 0 plus is? Yes, we do. It's 7, so that becomes minus 7, gives us 35 volts. So now that 35 volts goes into this equation, so we have that dI dt at time 0 plus. So the rate at which the current through the inductor changes at time 0 plus must then be equal to 35 divided by, what is the inductance? It's 0.4. 0.4, and that's quite a number, 87.5. 87.5, what's the units? Amps per second. Amps per second on that one. Right. So that sorts out that one. For dVdt, let's do that one quickly. How much space do I need for that one? Hopefully not a lot, because I don't have a lot. I'm going to rather do it over here. So, but I'm going to need this value. Hey? You've got that. You've got that. So I'm going to wipe this because I need the space. Right. So much for the board writing, so much better. Maybe it's the chalk anyway. Okay. So for dVc dt, how do we get that? From the current through the capacitor. So we know that the current through the capacitor equals C dVc dt. In other words, dVc dt at time 0 plus will be equal to IC at time 0 plus divided by the capacitance. Okay, so what is IC at time 0 plus? So what is this current at time 0 plus? So here we've got the inductor current, and from the previous calculation we got that current, and it was 3.5 amps coming in here. So this is 3.5 amps at time 0 plus. That 3.5 amps gets to this point. And now it needs to split between the 2 and the 2 ohms and the capacitor. So how much is going to go through the capacitor? How much is going to go through the 2? So to solve that, we need to do a KCL in this case. So now we're going to do a KCL for a change. We need to solve for current. So then we use Kirchhoff's current law. So all the currents coming in must equal all the currents going out. So what currents are coming in? We've got let's write it out first. So we've got IL at time 0 plus is coming in. That must equal IC at time 0 plus going out plus the current through the 2 ohms. So I'm going to write it as I2. But what is this I2? I need an expression for that one. To find the current through a resistor, I need to know what the voltage across the resistor is. Do I know the voltage across this resistor? Yes, we do, because it's just the capacitor voltage. So if I have the capacitor voltage, I can find the resistor current. Do I have the initial capacitor voltage? Yes, we calculated that as, what was it? 7 volts. So we know this is 7 volts for time 0 plus. So we can write, if we reshuffle this a bit, IC 0 plus must then equal, we keep it on the positive side, so IL 0 plus is 3.5. 3.5, we take the I2 over minus, and I2 we said is VC 0 plus. Perhaps, I'm substituting now already. So this I2, let's just write here, I2 equals VC 0 plus at divide by 2. All right, so then we know where it comes from. So it's 7 divided by 2. So that's 3.5 minus 3.5 gives me a 0 amps, which means this OK is going to be 0, because now I substitute the 0 into that one, 0 volts per second. So initially, the voltage across the capacitor isn't changing at all. Now, in terms of graphically, remember volts per second, it's a gradient here, so it's flat, 0 volts per second, 0 gradient. This one was 87.5 amps per second, so that's a steep uphill, so it's quickly going to rise. So the current through the inductor is going to start rising sharply. Okay, so that's the IDTs.
Now for the C part, we need to find the final conditions. Let's keep that one there. So now for the C part.
So what is I at infinity and what is VC at infinity? So our circuit is this, but now only it's in the steady state. So the capacitor will become an open circuit. So let's redraw that circuit again. See, I'm not lazy redrawing the circuits. Otherwise, I have to do it again next year. Well, then again, I'll have to do it next year anyway. But anyway, so the switch is still closed. The inductor is now a short circuit as well. And then plus minus. And it's still 42 volts, and that goes through, plus minus V The current is still in that direction, the current, and you've got your 2 ohms there. Okay, so how much current is flowing? What is the voltage? Well, let's write I infinity first. Well, there's only the one source and the one resistor in the whole thing. So I'm simply going to take the 42 divided by 2. Let me write it out. Divide by 2. Getting too short. Equals 21 amps. Okay, so that is what that current will be at time infinity. And then for V at time infinity, that one is even easier because you've got that 42 volts just sitting, it's in the way, the 42 volts just sitting parallel to your capacitor voltage, so that you simply just look at the circuit and you've got 42 volts. Right, so there we've got practice problem 8.1 done and dusted. I'm going to work through one more problem. How are we for time? Yeah, we've got a few minutes left, and I think this is a rather important one. Example 8.2. Yeah, so let's do example 8.2. In example 8.2, in addition to just the inductor current and the capacitor voltage, they also want the initial conditions for VR, this voltage across the 2 ohm resistor, and the dVR dt as well. So I'm going to show you how to do that. It's a bit, I want to say complicated, but then at least you've got one example on how to do that. Some of your homework problems require that, and yeah, you'll see where that fits in later on. We won't need it a lot, but yeah, it might come into play, especially in the general order circuits. So what we've got a current source that switches on at time 0. So there's a step function. There's a voltage source here, 12 volt, that's always on. But this one only comes on at time 0. So we've got a 2 ohm resistor, 4 ohm resistor, 0.5 farad capacitor, 0.6 henries. They give us the current direction through the inductor, so we can write there plus minus VL. And if that's the capacitor voltage, plus minus, we know the current will be coming down for the capacitor current. So again, let's just look at the initial conditions. So for I0 plus, we know that must be equal to I0 minus. So what does the circuit look like at time just before 0? Now, there's no switches now. We only have the step function. So at time 0 minus, this current source is still off, meaning it's an open circuit. So in that sense, our circuit will look as follows. We still have the 4 ohm. The capacitor will be an open circuit. You'll have still the, that's probably a bit too small for you guys. You still have a 20 volts sitting there, right? And then the inductor would have become a short circuit because at time 0 minus, we're in a steady state condition, steady state, so VC, and there we've got IL going through. And this is 20 volts. I hope you can't hear the chainsaw in the background, but this mic should help a bit. Okay, so this is still 2, and that's a 4. A 4. Okay, so what will this current be through the inductor? Well, looking at this circuit, now assuming there was energy stored in that inductor before, and now we've given this inductor a lot of time to discharge its energy and it's reached steady state, and there's only one path for this current to flow. So looking at this circuit, and you go, hi there circuit, my name is Dr. B, how are things flowing and going? Then you can see that there's only all of this energy would have been dissipated in these two resistors. So that would have to be 0 amps because there's not going to be any energy left in that inductor. The capacitor voltage is a bit of a more of a sneaky one. VC 0 plus equals VC. That we know, 0 minus. So what is the voltage in this thing? Now, it's just because the circuit elements are arranged a little bit weird that perhaps you don't see it the first time. but we apply our standard EBN circuit analysis techniques, and we are going to look for a voltage, so we do a KVL. So if we do a KVL in this loop, we've got minus 20, okay, minus VC, minus, let me just stand on this side, minus VC must equal everything 0, because it's a short circuit over the inductor, so that's a short. So in this sense, we can see that, hey, VC at time, we're just going to write that, then means that VC equals minus 20 volts. Okay, so that's for the first one. Then, or for the capacitor voltage. Then, what about that resistor voltage that's sitting over there, VR, at time 0 plus? Can we use this circuit? This is now a trick question. Where is this circuit is applicable at what time? At time 0 minus. You can't now go and say, oh, wait a minute, VR at 0 minus equals 0 bit time. Voltage over there at that resistor at time 0 plus must equal the voltage at time 0 minus. Why not? Because the voltage and the current for a resistor can change instantaneously. It's not like a capacitor and an inductor. So you can't say VR0 plus equals VR0 minus. So this circuit is not applicable for what we are looking for to get VR0 plus. To get VR0 plus, we'll have to go and redraw the circuit and see what it looks like for time greater than 0. Okay, so for now, let's just get rid of this one. And I'm just going to write in our initial condition for VC 0 plus, because we know we're going to need that value just now. It was minus 20 volts. Okay, so we're going to need that. Okay, so now let's go to the DIDTs, and then you'll see how we get the VR0 plus. I'm just going to close that window. Okay, so now we're going to do the DIDTs. So we know for the DIDTs already we're going to need the circuit at t equals 0 plus. So what happens then? At time 0 plus, that source kicks in. That one is still there. Capacitors there, inductors, everything is there at time 0 plus. So we just need this circuit diagram to solve for time 0 plus. So we don't need to redraw anything. We're just going to need use this circuit diagram with that current source now in. So let's start with di 0 plus dt, and that equals, now from, I'm not going to rewrite it again, so it's VL times 0 plus over the inductance. Did I start with that one? Yeah, okay. So I need to find the inductor voltage at time 0 plus in this circuit. So we're going to do a KVL again because it's a voltage that we need. So VL at 0 plus. So let's go through that loop. So plus VL minus 20 as we go in, minus VC at time 0 plus must equal 0. All of that must equal 0. Do I know what VC 0 plus is? Yes, it's minus 20 volts. So we're going to write VL 0 plus equals, we take the minus 20 over, it becomes 20. The minus over becomes a plus. But then VC 0 plus is minus 20. So that's minus 20. And 20 minus 20 gives me a 0. Volts, and if we plug that back into this equation, we get 0 divided by, I don't care what the inductance is, I get 0 amps per second. Amps per second. Okay, so there's that one. Then for the dVdt, let's do it over here. So for dVc dt at time 0 plus, we know that's going to be equal to IC at time 0 plus divided by the capacitance. So I need the current through this capacitor at time 0 plus. Now, this is where it might get a little bit tricky. Okay, and where the VR0 plus is going to come in as well. If I want the current through that leg, I know what this is at time 0 plus. It's 0 amps at least. But if I want that current, I need a KCL at that node over there, right? So let's write a KCL at node B. Right, yeah. So if you write a KCL at, I call this node B, and I'm going to make that node A. So KCL at node B will give me the following. All the currents coming in must equal all the currents going out. So what are the currents coming in? It's the current through this 4 ohms. So I'm just going to draw a current in that direction. So let's make it I4. I4 must equal IC plus IL. But now we know IL is just 0 amps. So if I can find the current through this 4 ohm resistor, I know what the current is through the capacitor. So effectively, because this inductor current is just 0 amps, it acts as an open circuit for that short period in time. Now, hold on there for perhaps just a moment. Did I just say that the inductor now acts as an open circuit? Remember, we're now not in a steady state condition. We're in a transient state, just at that moment when the transient is starting. At this time 0 plus, just after 0 plus, there's no current flowing. That we determined over there. Because there's no current flowing, the inductor then, where do you get 0 amps? In an open circuit. So it acts as an open circuit. So our new circuit is then effectively just this current coming in, splitting between the 2 and the 4, and is going to come down. So let's draw what that circuit is going to look like. So we redraw. It's going to look like this. We have the 2, we have the 4, we've got the cap, we've got the source over there, and it closes, and the inductor for now, there's no current flowing, so I'm just going to leave that part of the circuit, plus minus VC. Do we know what this is at time 0 plus? Yes, I know at time 0 plus that VC is minus 20 volts. I know this is 20 volts. I know that's been given as a 4, that's been given as a 2. This one is now on, so that is 3 amps. Okay. Now we're going to simplify the circuit even one step further. If that is minus 20 and that is plus 20, what is the voltage across between that terminal and that terminal now? 0 volts, right? 0 volts. Well, in this case, 0 amps gave me an open circuit. So if I've got 0 volts here, now what do I get? I get a short circuit. So we can simplify this part of the circuit to a short circuit. So now the capacitor becomes a short circuit. This is dear, eh? Right. So this is now actually what this circuit looked like. Now, what is it that we're looking for again here? We're looking for the current through the 4 ohm resistor. That current. Now, if you look at this circuit diagram, how easy is it to get the current through that 4 ohm resistor? It's just a current division. And I think perhaps amongst all the examples we've done so far, this is probably the one that the most clearly shows the importance of redrawing your circuit diagrams as you simplify them. And don't just look at this and think you're going to solve it, because what we've done now is to take this whole section of the circuit diagram and it's reduced to a simple short circuit. So you have to redraw. So in other words, from this, we get that I4 only at time 0 plus is going to equal that 3 amps. And then what goes through the 4 times the other one, 2 over 2 plus 4, 2 over 6, 1 over 3 equals 1 amp. So now we know what I4 0 plus is. In other words, IC at time 0 plus equals 1 amp. And that goes back into our top equation, which means that dVc dt at time 0 plus equals the 1, now let's write it out, 1 over what was the capacitance? 0.6. 0.6. Oh, no, man, this is not going to be a nice number. Oh, wrong one. 0.5. I'm looking at the wrong one, sorry. 0.5, thank goodness, because then we get a nice 2, what is it? Volts per second. Volts per second. That looks better. Okay. So this was quite a heck of a lot of work just to get this dVc dt. And when we get to the other parts of this chapter, remember just getting the initial conditions is just going to be part of solving the second order differential equation circuits. So this is a lot of circuit theory and circuit practice and insight into simplifying a circuit diagram so that you can just get to this part of the answer. Okay, in this process, we've got this VR as well, plus minus VR sitting there the whole time. And remember, they not only asked for I0 plus and VC0 plus, they're also asking for VR0 plus. So now in this case, we can actually calculate what is VR0 plus. It's going to be the current through this 2 ohm times 2. So how much current is flowing through this 2? Well, if there's 1 amp going through the 4, it means there must be 2 amps going through the 2 ohms. So 2 times 2 equals 4 volts. If you missed that one, rewind and just listen to that again. All right, so VR0 plus equals 4 volts. And we've got dVc dt now, so that's sorted. So now we're left with, oh no, there's still the final conditions that we have to, didn't they ask for that? Okay, now let's work with dVr. You know what, for this lecture I'm seriously running out of time, but this is actually the most difficult part of the problem. So I do want to work through this one. You know what, it's an example. So I'm going to leave it for you guys to work through the dVAB dt or the dVr dt part in the textbook example. I think we'll have time to do that in a later stage. I want to finish this one by calculating the final conditions for the capacitor and the inductor. So let's
work on that. Otherwise, this lecture is actually already too long. Okay. Yeah, in the class I would have had to stop by now because you would have had to run to the next class. So for the C part, let's just look at I infinity and VC at time infinity. So now the capacitor will become an open circuit. I'll clear this a little bit. So what is our circuit going to look like? The current source is still there. The resistor is still there. Then we've got that resistor is still there. The capacitor is now an open voltage with that voltage source still sitting there. Lovely circuit, hey. Anyway, okay. Doesn't work with my hands on this board. Works in class. And then the inductor would be a short circuit. Okay. 3 amps, 2 ohms, 4 ohms. Plus minus VC. Okay. So what will the final conditions be?
If you look at this circuit, so the 3 amps is going to come. It's going to split between the 2 and the 4. And then it's going to get to this point. It sees an open circuit and a short circuit. So it would seem the 4 ohm current will be the same as the inductor current. So I infinity is going to be the 3, and it's going to split between these two. So it's going to be the 3 times 2 over 4 plus 2, and we get 1 amp. I mean, I'll write, yeah, 2 over 6, 1 over 3, and I get 1 amp flowing through that one. Then, for the capacitor voltage, what will that be at time infinity as the current flows? Well, this capacitor will charge up, it becomes an open circuit, and then we see if we do a KVL in this loop again, so that, remember, that's 20 sitting over there. We still have to, the KVL still has to hold in this circuit, so it's pretty much the same as what we had before we switched in that, okay. So it becomes a minus 20 again. V infinity equals minus 20 volts. All right, so that then sorts out this problem or the example in terms of the final conditions as well. I will then see you in the next lecture for starting with source-free RLC circuit. Sorry for the bit of a long video, but yeah, we need a lot of practice, and we'll definitely do a lot more of this when we as we go into the next sections of this chapter. All right, thanks a lot, and you'll see me in the next one. Bye bye.